編集はい、ではアシュクロフトマミンを始めます。今日は10ページからということなので、ここにアシュクロフトマミン10ページ、ここに PDF があります。10ページはほれほれほれという感じで、3、4、またファンがすごい大きくなってる音が。なんでだろうね。two cases of particular interest are calculation of the electrical conductivity when a spatially uniform static magnetic field is presented and when the electric field is spatially uniform but time dependent. Both of these cases are most simply dealt with by the following observation. その前にこれをやっただけドゥルードrelaxation time in units of 10 to minus 14 seconds. So this is more random. Relaxation times are calculated from data in table 1.1 and 1.2 and equation 1.8. The slight temperature dependence of n is ignored. I think electrical conductivity is more regular, how to say, because this value is almost 1. So this is almost 1. So temperature dependence is quite linear for the electrical resistance or resistivity. Resistivity is more linear temperature dependence. Yeah. So then what about the scattering time or relaxation time? There's no linearity discussed here. So it just say maybe the relaxation time is order of 10 to minus 14. 10 to minus 14. Some of them are 10 to minus 13 or 10 to minus 15. 10 to minus 15 or 10 to minus 16. Yeah. What is the highest, largest scattering time? The kappa, 77 Kelvin kappa is 21. And room temperature, it is silver. I heard silver has the lowest electrical resistivity. Is this correct? Silver is silver. Silver is 1.56 or 1.51 at room temperature at 373 2.13 micro ohm centimeter. So let me, this is silver. At least at high temperature, it is the lowest. Let's see. Yeah. At low temperature, 77 Kelvin, copper is lower. Electrical resistivity of copper is lower than silver. Aluminum. Oh, sorry. Okay. At any time t, the average electronic velocity v is just p over m, where p is the total momentum per electron. Hence, the current density is J equal minus NEP divided by m. Given that the momentum per electron is p at time t, let us calculate the momentum per electron p or at t plus delta t an infinitesimal time dt later. An electron taken at random at time t will have a collision before time t plus dt with probability dt divided by tau, and will therefore survive to time t plus dt without suffering a collision with probability 1 minus dt divided by tau. If it experiences no collision, however, it simply evolves under the influence of the force Ft due to the spatially uniform electric or magnetic field, and will therefore acquire an additional momentum Ft dt plus order dt square. What is footnote 12? By order, big order big O of dt square will mean a term of the order of dt square. The contribution of all those electrons that do not collide between t and t plus dt to the momentum per electron at time t plus dt is the fraction 1 minus dt over tau. They consist constitute of all electrons times the average momentum per electron. The contribution of all those electrons that do not collide between t and t plus dt to the momentum per electron at time what is they? The contribution of all those electrons that do not collide between t and t plus dt, the momentum per electron at time t plus dt is the fraction 1 minus dt over tau. They constitute of all electrons times their average momentum per electron p plus ft dt plus big O of dt square, thus neglecting for the moment the contribution to p of t plus dt so this has to be italic, I think. This has to be italic. From those electrons that do undergo a collision in the time between t and t plus dt, we have p t plus dt equal 1 minus dt over tau times p plus ft dt plus big O of t dt square equal p minus dt over tau p of t plus ft dt plus big O of dt square. What is footnote 13? If the force on the electrons is not the same for every electron, 1.10 will remain valid, provided that we interpret F as average force per electron. don't understand. Contribution of all those electrons that do not collide between t and t plus dt to the momentum per electron at t plus delta t is the fraction something seems I would say I would delete this. Momentum per electron at time t plus dt is the fraction 1 minus dt over tau of all electrons times their average momentum per electron pt plus ft dt plus big O of dt square. The correction to 1.10 due to those electrons that have had a collision in the interval t to t plus dt is only of the order of dt square. To see this, first note that such electrons constitute a fraction dt over tau of the total number of electrons. Furthermore, since the electronic velocity and momentum is randomly directed immediately after a collision, each such electron will contribute to the average momentum P of t plus dt only to the extent that it has acquired momentum from the force since its last collision. Such momentum is acquired over a time no longer than dt and is therefore of order ft dt. Thus, the correction to 1.10 is of order dt divided by tau ft dt and does not affect the terms of linear order in dt. We may therefore write p of t plus dt minus p of t equal minus dt over tau pt plus ft dt plus big O of dt square, where the contribution of all electrons to p of t plus dt is accounted for. Dividing this by dt and taking the limit as dt go to 0, dpt dt equal minus pt over tau plus ft. This simply states that the effect of individual electron collisions is to introduce a frictional damping term into the equation of motion for the momentum per electron. We now apply 1.12 to several cases of interest. Hall effect and magnetoresistance. In 1879, E. H. Hall tried to determine whether the force experienced by a current carrying wire whether the force experienced by a current carrying wire in a magnetic field was exerted In 1879, E.H. Hall tried to determine whether the force experienced by a current carrying wire in a magnetic field was exerted on the whole wire or only upon what we would now call the moving electrons in the wire. Exerted on the whole wire or only upon the moving electron in the wire. He suspected it was the latter, and his experiment was based on the argument that if the current of electricity in a fixed conductor is itself attracted by a magnet, the current should be drawn to one side of the wire, and therefore the resistance experienced should be increased. Complicated. He suspected it was the latter, and his experiment was based on the argument that if the current of electricity in a fixed conductor is itself attracted by a magnet, the current should be drawn to one side of the wire, and therefore the resistance experienced should be increased. I don't understand. His effort to detect this extra resistance were unsuccessful. The increase in resistance, known as the magnitude resistance, does occur, as we shall see in chapters 12 and 13. The Drude model, however, predicts Hall's null result. ちょっと待って。どういうことだ？Hall tried to determine whether the force experienced by current carrying wire in the magnetic field was exerted on the whole wire or only upon that we would now call the moving electron in the wire. He suspected it was the latter, and his experiment was based on the argument that if the current of electricity in a fixed conductor is itself attracted by a magnet, the current should be drawn to one side of the wire, and therefore the resistance experienced should be increased. I don't know, maybe this is like this. If you have wire and there is an electron, then you have magnetic field, something like this. So this magnetic field exert force whether either on the whole wire or this magnetic field exert force on each electron moving inside the wire, I think. And Ho suspected it is the latter. So this magnetic field exert force to the electron inside. So this, I think this electron, like the path of electron is deflected. Then he says the current should be drawn to one side of the wire, therefore the resistance experienced should be increased. Okay, so because this electron path is deflected, so that maybe the resistance should increase. His efforts to detect this extra resistance were unsuccessful. But Ho did not regard this as conclusive. The magnet may tend to deflect the current without being able to do so. The magnet may tend to deflect the current without being able to do so. It is evident that in this case there would exist a state of stress in the conductor, the electricity pressing as it were towards one side of the wire. The magnet may tend to deflect the current without being able to do so. It is evident that in this case there would exist a state of stress in the conductor, the electricity pressing as it were, toward one side of the wire. There will exist a state of stress in the conductor as it wereってなんだっけ、いわばelectricity pressing toward one side of the wire. This state of stress should appear as transverse voltage, known today as the Hall voltage, which Hall was able to observe. Hall's experiment is depicted in figure 1.3. An electric field EX is applied to a wire extending in the x direction and current density Jx flows in the wire. In addition to a magnetic field H pointing in the positive z direction as a result of the Lorentz force, minus E divided by C V cross H acts to deflect electrons in the negative y direction. An electron drift velocity is opposite to the current flow. However, the electrons cannot move very far in y direction before running up against the side of the wire. As they accumulate there, an electric field builds up in the y direction that opposes their motion and their further accumulation. As they accumulate there, an electric field builds up in the y direction that opposes their motion and the further accumulation. That opposes their motion and their accumulation. In equilibrium, the transverse field or Hall field EY will balance the Lorentz force, and the current will only in the x direction. Schematic view of Hall's experiments. There are two quantities of interest. One is the ratio of the field along the wire EX to the current density. Rho of H equal EX divided by JX. This is the magnetoresistance. Number 17. Number 16. When dealing with non-magnetic or weakly magnetic materials, we shall always call the field H, the difference between B and H being extremely small. Number 17. More precisely, it is transverse magnetoresistance. There is also longitudinal magnetoresistance measured in the magnetic field parallel to the current. The two quantities of interest. One is the ratio of the field along the wire EX to the current density JX. Okay, this is the magnetoresistance, which Hall found to be field independent. I don't know what I wrote. The other is the size of the transverse field EY. The other is the size of the transverse field Ey. Since it balances the Lorentz force, one might expect it to be proportional both to the applied field H and to the current along the wire Jx. Therefore, one defines a quantity known as the Hall coefficient by RH equal Ey divided by Jxh. Note that since the Hall field is in the negative y direction, 1.3, RH should be negative. If, on the other hand, the charge carriers were positive, then the sign of their x velocity would be reversed. And the Lorentz force would therefore be unchanged. As a consequence, the whole field would be positive to the direction it has for negatively charged carriers. This is of great importance, for it means that measurement of the whole field determines the sign of the charge carriers. Hall's original data agreed with the sign of the electronic charge later determined by Thomson. One of the remarkable aspects of the Hall effect, however, is that in some metals the Hall coefficient is positive, suggesting that the carriers have a charge opposite to that of the electron. This is another mystery whose solution had to await the full quantum theory of solids. In this chapter, we shall consider only the simple Drude model analysis, which, though incapable of accounting for positive Hall coefficients, is often in fairly good agreement with experiment. Which is though incapable. To calculate the Hall coefficient and the magnetoresistance, we first find the current density Jx and Jy in the presence of electric field with arbitrary component Ex and Ey. To calculate the Hall coefficient and magnetoresistance, we first find the current density Jx and Jy in the presence of an electric field and arbitrary components Ex and Ey. But there is and in the presence of a magnetic field H along the z-axis, the position-independent force acting on each electron is F equal minus E, electric field E plus V times H divided by C, and therefore equation 112 for the momentum per electron becomes 18. Note that Lorentz force is not the same for each electron since it depends on the electronic velocity v. Therefore, the force F in 112 is to be taken as the average force per electron, see footnote 13, because, however, the force depends on the electron on which it acts only through a term. The force depends on the electron. Force depends on the electron on which it acts only through a term linear in the electron's velocity. The average force is obtained simply by replacing that velocity by the average velocity, P over m. Okay. どうしようかな。So I want to break it here. So let me stop today. Then probably I can continue quite soon. So I break for